Hey guys, this is Terrence and welcome to the new episode of RhinoPython and GhPython Playground. And yeah, this is our today's pattern. I call it the folding wall. This pattern is basically based on the voronoi pattern, but on each cell I provide two options. The first one is to create this kind of ridge-like cell. Another one is to create this kind of jaggy or folding volcano shell. So let me bring up the Illustrator file to show the process of creating this pattern. So the first step is, as we have this outline, this voronoi outline, we can extract its vertices and move each of the vertex upward a little bit. And to create a new polyline like this, all the points moved in a random distance, so the new polyline will not locate in the same plane. I just want to make the pattern more dynamic by doing so. When we have our new cell, we can start creating our own cells. The first cell or the first option I call it the ridge, which means the pattern has an obvious ridge here. The first step of creating this cell is we need to find the centroid and move the centroid upward a little bit, and also move it along the base plane. Make it have a three-dimensional position. Make it have a position shift in three-dimensionally, I think. Yeah. So we should extract the start point, we should have an end point, and along with the updated centroid, we can create a curve. With the new curve, we can convert it to this kind of jaggy polyline. Then we can loft this half of the polyline with the jaggy polyline, and loft the jaggy polyline with the rest half of the original cell. Then we will get this kind of cell. For the volcano one, we need one more step, which is we extract all the vertices and move it inward. Use the updated vertices to create a new Nurbs curve. And also we need to find the centroid and create a circle along the centroid. The next step is we need to lift this newly generated Nurbs curve, then convert it to the jaggy pattern or to the jaggy polyline. Then loft the outline of the voronoi cell with this jaggy polyline, and loft the polyline with this center circle, and then we can get this volcano pattern or volcano cell, sorry. So let's start working on the Rhino grasshopper and our code. Yeah, I should be careful not make my head block this window. Yeah. So before I started, I want to mention that I made two changes on this series video. The first one is I switched from Windows to Mac, and you can see I have the interface, the Rhino interface on Mac is quite different from the Windows. I think this one is much more cleaner and and it looks better, I feel. Yeah, but don't worry, everything keeps the same as the Windows. I mean, although the interface is different, but you can get the same results by following by doing the same thing. So don't worry about that. The second change I made here is that I think in the most of my previous video, I only stick on the RhinoScript syntax library. RhinoScript syntax library, but from this video on, I will use this Rhino.geometry library srg. Import Rhino.geometry srg. This is basically the Rhino common based library. It's powerful than the RhinoScript syntax, which is just a functional based library. The Rhino common library is object oriented, is super clean, super powerful, and will make my code very organized. So from this video on, I will gradually deprecate all RhinoScript syntax in my video, and will stick with the Rhino geometry library. So yeah, so we can start creating creating this episode's pattern. First, I think we need to have a voronoi pattern as our base. So I need to have a rectangle node here. Let me zoom in a little bit and make the x dimension as, no, 600 is too big, as 60. Make the y dimension the half of 60, which is 30, and we will have this small rectangle here. Then we have this boundary. We need to populate some points. I can say populate 2D here and connect the region to this end. Now we have 100 points. I think that's fine, and we should create a voronoi pattern with the voronoi node. Also connect the region to this boundary, and we will have our voronoi pattern just limited in our rectangle or in our site. But one problem here is that now our pattern is evenly distributed, which is fine, but I want to make it more dynamic, so I want to add, let me increase the size of this window. Let me add one more node, which is called random reduce, I think. Yeah, random reduce. Connect the point to the list, and then I need to have a multiplication node to define the number of points I want to reduce. So so for this node, the A input could be the length of the number of points. So this should be the list. This should be the list length node. Can help me get the number of the points and put this value to the A end. And for the B end, which is another value for the multiplication, I want to set it between 0.1 and 0.9. And connect to here. I think the random reduce now is not working. And if I connect the updated point list, I will get the updated pattern. But it's not so obvious for now. I just want to make all of the previous nodes invisible, and yeah. Now let's move this value. Let's change this value to see what changes take place. So if I increase the number, increase the number of points to reduce, we will get more this kind of more dynamic pattern. I think more unevenly distributed pattern, and I think this one is somewhat fine. So we have our base voronoi pattern. We can start working on this one. Then I need to create a GhPython node here, and yeah, and show code input parameter, and input is path, because I always work on the external editor. I don't want to just work in the this grasshopper space. It's super inconvenient. And for the first input, I want to set it as cells, CELS, cells. Right click it, set to the list access, and the type hint should be curve. Yeah, because this polyline belongs to polyline curve belongs to the polyline curve object in the Rhino common library. So I can connect it to here, and I want to have a new node called file path, which connects my GhPython node with the external Python file. Yeah, I should set it as synchronize and select one existing file. On desktop, I think this one, folding.py. Yeah, connect it to here. Anything wrong? No script executed. So let's first try it out. Now I should move the map here. Oh, I don't want my head block this grasshopper map, and I can create a panel connect to this node to show the result, I think. And then let me write the first line of code to test, are these two files connected? I can say print test and save it. Yeah, the test popped out, so we can start working on the code to create the pattern now. And I think the first thing we need to do, let me bring up this again. The first thing we need to do is to update the position of these vertices, then create this new series of non-coplanar polygon or non-coplanar voronoi polygon. So I think we should define our first function, which is called move vertices vertices yeah vertices, and the input should be a polyline. Let me double check the file the type here. Yes, it's curve. So the first thing is we need to find how many points in each of the polygon, then loop over all of the points, update its position. So our first step is we should find the number of the points in the polygon. We should say polyline dot point count, I think. Yeah. Then we need to declare a new empty list to contain our updated points. We also need to have empty list to contain our plans for the future modification or for the future transformation. So if we can store the plan information here and return it somewhere at the end of this function, we will be more flexible in controlling the whole pattern. And then we can start to loop over each of the points on each of the polygon. I can say for I in range pt number, and just let points dot append polyline dot point at position I. So first step, we need to extract all of the points into the PTS list. Then we can update the locations, the position of each point. Then we can say if to find a plan, we need at least 3 points, right? So we can say if the length of the points is smaller or equal than 3, we can just say, sorry, I think I need to change this a little bit. I need to say this as plan points instead of a plan, because I just add 3 points into the plan points, then use the 3 points to calculate a working plan. So which is for plan points smaller than 3, I can say plan pts dot append pts I, right? And then next step is we need to generate a plan based on, sorry, I think it should be unindented here. When we have all the points and we have 3 points for the plan, now we need a plan, right? Equals to rg dot plan. We can generate a plan from 3 points. The first one is plan pts 0, plan pts 1, and also plan pts 2. Now we have our plan. The next thing is we need to update the all of the points position. So we need another loop. We can say for I in range pt number. We should randomly define the moving distance. So maybe I need to import the random library here, random. Yeah, I can say scalar equals to uniform from 0.0 to 2.0, which is the range of my moving distance. Then I can say vector, which is moving vector, equals to plan dot, I want to move it along. I want to move it on the z-axis of plane, the plane might be this kind of xy plane or yz plane. So the z-axis will be always perpendicular to the plane. I want to move it along the z-axis, so I can say z vector equals to plane dot z-axis. Yeah. Then yeah, we can use this vector to multiply our scalar value. Then we will have a scaled moving vector. Then we can update our points location. We can say ptsi equals to ptsi plus vector. Then let me see. Yeah, because we are looping over the points on the closed polyline, which means the last point is identical. The last point's position should be identical to the first point's position. So at the end of this function, I mean the last step, we need to ensure the first point and the last point are exactly the same. So I can say pts -1 equals to pts 0. Then at last I can just return the points and the plane as well. I think we can just test this function a little bit. Let me organize my code, and I want to make a comment here. Say step 1, moving vertices, CES, vertices. Oh, can I find the right spelling? Vertices. Yeah, it should be vertices. CES is enough. So I think let me first test this out in one of the polygon. And I can say A equals to move vertices, VERTICE, vertices. The input polyline could be cell, maybe with index of 5, and save it. Let me see. Oh yeah, I should say cells. Uniform is not defined. Uniform. Oh, I should say from random import everything and save it. I think this should work now. And where is my new polygon? Yeah, here it is. I think okay, I got it. I know what's happening here because yeah, because the first value is now RhinoPython list. In the RhinoPython list format, I need to convert it into the points style. Maybe if I add this one, yeah, I will have these new points, and if I connect all the points as a polyline, I think I will get the result of our first step. Yeah. So don't worry about this kind of uncoplanar distribution. This is what we want. We will create some dynamic pattern based on this unevenly distribution. So if we change the cell, I think we can get different results. Yeah. So what about for the 9? Yes. Yeah, we basically have what we want now. And I think the next step is we can start creating our first cell. Let me bring up this Illustrator file again. So the first step is based on the vertices we provided. We can calculate the center point, then create this kind of curve. At last, we will have these jaggy polylines. So maybe we need to define another function. I will make a comment, say step 2, cell type A. Oh, sorry. Cell type A. And divide polygon. we should have two inputs. The first one is vertices, and the second one is a working plan. Like we just we returned from this move vertices function. And in this inside this function, the first thing we need to do is to find the centroid, start point, and also the end point, just like here. We need centroid, start point, and end point. So let's first find the start point and end point. So my solution is I will set the start point as the first point in the vertices vertices 0. This is the first point in the vertices list. I define this point as our start point, and the end point could be vertices. We should provide some index here, but my custom is like I want to set a mid index, which is maybe the middle point inside the whole point list. Then I can ensure I can create this kind of curve that spans from one to another side of the polygon. So I'd like to say the mid index might be length of vertices integer divided by 2. Then I can input this mid index mid idx as this index number. Yeah. So we have our start point, we have our end point. Then we need to get our centroid. To get the centroid, I prefer to define a new function called get centroid, and I should provide some vertices here. I will use the average way to calculate the central point. So inside this function, first I need to define the center point as a list. To declare the center point as a list, I want to say centroid equals to a list with 3 numbers inside it. All of 3 numbers are 0. Then I can start loop over all the vertices. I can say for I in range length vertices, but -1 because I don't want to calculate, because I don't want to include the last point into this process, because the last point is is identical to the first point. If I add that to this computation, that will make my center point shift a little bit to the start point, and that is unwanted. So yeah, I want to exclude the last point. So inside here we can say centroid 0 plus equals to vertices I first value, and I can copy this line of code, paste it 3 times. Sorry, I shouldn't do this. Okay, paste it and change the value inside here. Here should be 1, and this one should be 2. 1 and 2. Yeah. And after we have this updated and summed centroid, we need to divide each value by the length of vertices -1. So we can use a list comprehension. We can say centroid equals to value divided by the length of vertices -1 for value inside the centroid. Yeah. And then we can return the center point. We can return the center point by saying rj.point3d with 3 value. You can see here x, y, and z. So I can do point3d centroid index 0, centroid index 1, and central index 2. Then I think I will have my have my centroid function down here, then I can say centroid equals to get centroid and place the vertices into this function and save it. See, are there any problem? No. And yeah, I just see the shape slightly changed because the distance is random. I don't want this change take place frequently, so I want to set the seed as a fixed number, maybe 1,100. Yeah, 1,000. Yeah, that's fine. So every time I save, the pattern will not change. So we have our center point. Now we need to test this function out. I can say what? I can say this one. So let's first test this get centroid function. We can copy this function name here and say a equals to get centroid a. If we can have this, yeah, we have this centroid here. And if am I doing something right? Am I choosing the right cell? Okay, we can test it here. I can say move vertices and a equals to divide polygon with a, and with a as our, no, it's not clear. We should make the whole process more clear. We can say test polygon equals to this one and put this variable into our divide polygon function. And the second one is the plan, which is I can remove this index. I can say this one is index 1, index 0, and the second input could be test polygon with the index of 1, and maybe we can have a new updated result. Now, yeah, we didn't really return everything. I can just return centroid. And am I really have the centroid here? Let me double check the code again. Oh, no, not this one. I can say this one. Save it, and yeah. Oh yes, it's here now. I just forget to wrap this part of code into a function, into a parenthesis, so that makes some problems. Yeah, please be careful about the calculation sequence or calculation hierarchy. And now we have the centroid, we have our start point, we have our end point. We can start to shift, to move the position of the centroid and use these 3 points to create a ridge line or a curve. So let's go back to this divide polygon function and start updating this centroid position. So we can just create 3 offsets along 3 axes of this plan. We can say x of equals to plan dot x-axis, plan dot x-axis multiplied by uniform, FORM, uniform, range from 0.0 to 2.0, and we can do the same thing on the y-axis and z-axis. It's x of, it's y of, and it's z of. And we don't need to change the value on x and y of, but for the z offset value, I want to make it a little higher, so I will change the uniform range from 1.0 to 3.0. Then we can update the centroid's position by just updating each of the coordinate value. I can say centroid 0 equals to centroid 0 plus x offset, and do the same thing on the y and z axis, y and z coordinate. 1, and this time this should be y, this should be z, this should be 2 and 2, and now we have our updated centroid position. Let me save it. Oh, there's something wrong here. Float and vector 3D plus equals to. Oh, sorry. I'm so stupid here. I should say x of y of. Yeah, they are. These value are vectors. Let me just print this out, and you will know what's wrong. What the problem I make here. X of. And actually, you can see there are 3 values here. That means this is a vector instead of just a float value. So I should do something like this: centroid 0 plus x of offset 0 plus y offset 0, then plus z offset 0. I want 3. I want the translation on 3 axes happens on this on each of the coordinate value on the centroid. So I should do the same thing in the following 2 lines. On the following 2 lines, okay, 1 and 1. I should do this here. I should say this one 2 and 2 and 2. I think then I will see the updated result. Yeah, you can see it's swift. It's slightly switched from its original position, but I feel the distance might be too large. It's already invaded into other cells, so maybe I need to decrease the offset value a little bit. Is it enough? No, it's still not enough. Make it 0.5 and 0.5. Okay, still too large. It's unexpected. Yeah, so I think we need to make it even smaller, maybe. Let me check the height. The height is just well. So maybe I need to... Yeah, should I keep reducing the number? I feel it's already very small, but yeah. I don't think it will be so big. I mean just 0.1, but why the position shifts so large? Equals to, if I simplify this part, I call plus equals to this one, z offset plus equals to. Oh yes, I think I find the solution here. No, nothing changed. Okay, let me just update this pattern and try, and maybe have a try a smaller value like 0.05. 0.05. This is not what I want. Sorry, I'm so stupid. Yes. Yeah, this time it works, and I should change it to 2.0 here, 2.0 here. I'm so careless. Reduce the number could be an option. Reduce the value and 2, 1 to 2. Yeah, and still too high. 1, but 0.5 here. Yeah, I think this distance makes a lot of sense. Okay, so now we have 3 points, right? We have our start point, we have our end point, and our centroid. Now we should create a curve based on these 3 points. So we can say curve equals to rg dot curve class, and then create interpolate curve with these 3 points. I want to start from this start pt and set the centroid in the center, then ends up with this end pt. And yeah, let me see. Unexpected got point 3D. Oh, this input should be a list, so I can wrap this three value with a square bracket and at least two arguments. The first one, let me see. Yeah, I need to input a degree. So the first input are these 3 points. The second input should be the degree. I will set it to 3, and then we can return this curve to see the result. Okay. No, it's not. It's Oh yeah, it's actually right because I still need to input. I still need to show the updated vertices. So here I want to say I want to create an output here and show you guys the updated polygon b equals to test polygon 0. Is it 0? Yeah, I think it's 0. Yeah, so you can see these are updated vertices, and this is my newly generated curve. Let me double check this. Yeah, scalar. Are they coplanar? Polyline to check it. No, they are not coplanar, but just has a very nuanced distance in height. But that's fine. That's fine. And now we have this curve. We have this polyline. We need to. The next step is we need to make this curve jaggy. So we need to define a new function to process this newly generated curve. I want to divide this here with a comment. I call it helper functions. So the first one is get centroid. The second one is to jag curve with an input of curve and jag curve. I need a working plan as the second parameter. I need number of divisions, and also I need yeah, I think we just need these three parameters for now. And inside here, I want to first divide the curve by length. I don't want to divide it by number because the curvature, because the curvature is changing. If I divide it by number, we will have a denser point distribution here, but a sparse distribution in this side. So I want to divide the curve by length, which will create a evenly distributed subdivision. So first thing, I want to calculate the total length of the input curve. So I can see total length equals to curve dot get length, which is a function. Then I will find the step of the subdivisions. I can say length step equals to total length divided by divisions. I think I can start inject this function into these divide polygon functions. Then I will know are there problem take place. I want to first save these files, save it, and save it. So I should say curve equals to jag curve. With the input of curve, the plan, where is the plan? Yeah, we have plan input here, so we can place the plan variable here. Then third input, maybe, sorry, maybe this time I want to make it 24. Yeah, make 24 subdivisions. So I will test it out. I will test the length. Division is not defined. Divisions here, yeah. And I will try to print out this length step to see the result. Yeah, I think I have what I want. Then we can keep going on. We have our total length, we have our length step. So we need to calculate the t value, the parameter value on each step. Then we can use the perimeter value to create to find the curvature, which is a key vector to move the point. So I can say t is equals to curve dot divide by length, and the first input should be length step. The second input should be true, which means include the end. But the problem is, let me save this first. The problem is when we check the file, the data type of these t's, we will find it's actually the array float, which is a C# structure. It doesn't allow me to add value inside it because I need still to add the last point into this list. So in this condition, I want to convert this array float list into our Python list, which will be more flexible. So I want to say ts equals to t for spelling issues, t for t in t's. Then if we print this value, we can see now it's converted to the GhPython list. And yeah, we have all this value here. Oh yes, for this condition we don't need any other process, but for the next cell, for the cell B, we will need extra steps. But yeah, we just leave it here and keep going on our first cell. And now we want to have the offset distance, which is the jaggy distance here. That means how long, or that means how much distance we should shift we should shift every other point from its original position, then create this jaggy pattern. So we need to have a distance, right? So the distance should be, we call it off distance equals to a uniform, ranges from maybe 0.1 to 0.3. We can make it small, and we can also modify this value in the future. And then we create an empty list to contain the newly generated point. Then after this step, we can start to moving the curve, moving the points on that curve. So we can say for I in range length ts, and for t value, which is perimeter value, equals to ts with index I, and we have our curve, we have our perimeter. Now we need a point. We can say new pt equals to curve dot point at index I, and should be point at t. This should be a perimeter instead of index. Yeah. So we don't want to move all the points, right? We just want to move every other points, which means if the index of the point is like 0, like 2, or any other even value, we don't move it. But if the index is the odd number, like 1, 3, we will move the point. And another thing is, we will not move the point at the two ends, so we need to set up a condition here. We can say if I modulo by 2 is not equals to 0, which means the index is an odd number, and the index is not the last point, ts -1. Yeah, I should wrap this expression with a parenthesis. And when these two conditions fulfilled, we can move the point. We can say moving vector equals to curve dot curvature, curvature at curvature at this parameter. Then we will unitize this parameter. We should say vector dot unitize, And then we want to merge this vector with the z vector, with the plan's z vector, to make it slightly move away from its curvature direction to a little close to the z-axis of the plane. So we can say vector equals to negative plane dot z-axis plus vector. So we have the moving vector, we can start updating the position of the point. So the point could be vector. What we have now? No, I think vector equals to yeah. Here we need to scale this vector to the this offset distance. We can say off vector equals to vector multiplied by offset distance, I think. Then we can update the vector's position. I can say new pt equals to new point plus vector. And I think all of this should goes under this if condition. Yeah. And yeah, no error happens. That's a good news. Then we can just append the new point into this point list. So we can say points dot append new pt and then return these points. Yes, we have this one, but oh yes, here are the new pattern, and why it shows up here. In which way I define this part? I think it's a and divide polygons. Oh yeah, I update all these points here. So let me test this out to see if every point is on the correct position. I think so. And I don't know, is this jaggy pattern too exaggerated, but I want to just leave it here. And then now for the next step is now I have this jaggy polyline, and also yeah, I always need to bring up this one. We have this jaggy polyline. We also need to have this half of the polygon and another half of the polygon. So we basically need to return 3 polylines: the first half, the jaggy one, and the second half. So inside here we can say let's go back to the divide polygon function and try to extract the other 2 polylines we needed. Now we have this one, we have this curve. We first need to convert these points into the polyline. So we should say curve equals to rg dot polyline curve, and place all the points into this polyline curve. Then we will have this polyline, which is what we want. Then we need to have the first half of the polyline, or of the polygon. So we can say half a equals to rg dot polyline curve, with the vertices ranges from the first one to the mid index. CES equals to the from the first one to the mid index, but I want to make this mid index inclusive, so I need to plus it with 1. And for the half 2, for the half b is another half of the polygon. We should say rg dot the same thing, polyline curve with vertices ranges from mid index to the end. And then along with this curve, we should return half a, half b along with this curve. And my way of format is to put the curve at the first place, then half a and half b, return them as a list and save it. And you can see now we have these 3 polylines. If we check the data set, you can see we have this. Oh, I can zoom in a little bit. We have 3 polylines. Now let's test these 3 polylines out. Let's see, can we create a lofted solid pattern with these 3 polyline? We can just list item here, list item, and connect it to here and add 2 outputs. The first one is our curve, while the second and third one are 2 halves of this polyline. So I can say loft the first one with the first half at first, and yeah, it works pretty well. And let me try another one. I know it will cause some problem, but yeah, I prefer to do it to see what's going on. And you can see it's actually why don't I bake it? Why don't I bake this one and make it invisible? And you can see this half works very well, but this half it looks very weird because the direction of this curve was flipped, or it's inversed from this half. So we need to first reverse the direction of this half, then we will get a right result. So let's remove this one and show the result here, preview the result here. What we need to do is just to reverse this half b here. So we just need to say half b dot reverse. Save it, and oh, SE spelling issues. And you can see now we basically have the right cell we need. So we have our first cell now. We can start working on our second cell, which is this volcano pattern. And the first step is we need to move each of these vertices inwards, and we also need this center point, this centroid, and the circle in the center. So let's define another function for our second cell. We can say this should be, I call it step 2. So here should be step 3, and cell type B, and we call this function as offset polygon. Offset polygon. Yeah, I think I spelling right here. Vertices as first input and plan as second input, which is very similar to our previous one. So inside here, we need to first get a centroid equals to get centroid here with input of vertices, because we define this function here, so we can just recall this function again. We don't need to write an extra code or repetitive code. Then we want to have this. We want to have 2 things. The first thing is this shift distance. Another thing is this lift distance. So basically we need 2 distance here. 2 distances here. So first we can say distance. This is a horizontal distance, which could be uniform. Ranges from 0.3 to 0.4, I think. And another distance is called I can call it height, which equals to uniform spelling. I always have a lot of spelling issues. It ranges from 1.0 to 2.0. I want it corresponded to this part. So 1 to 2 might be too large. I can say 0.5 to 1.0. And we have distance, we have centroid. Now we need to move each of the vertices inwards. So we need new points. So we declare a new point list here, and we can start loop over all the vertices. So I can say for I in range length vertices. We can say V as our current vertices, and we want to have a moving vector, which is, let me show you this. We can have a moving vector which moves from these vertices to the centroid. So we need to subtract this point to get moving vector. And I want to say vector equal moving vector equals to the centroid, which is our target location, minus the current location, and multiply by distance. So distance here is basically a factor instead of an exact distance. So the 0.3, 0.4 means somewhere between 0.4 and 0.5 of the whole distance. It's not an exact distance, but just a relative one. Yeah. And also we need to vector add plus plan dot z axis, which is moving our point upwards here, and multiply by height. This height is the absolute value because this z-axis is an unitized vector, the length of which is just 1. If we multiply 1 with the height, we will get the exact value. Then we can just update the current vertices position with this vector. So I can say new pts dot append current vertices with a new vector, and I think I will get a new list of points. I want to test it out here, and this time I can just say I can change the function from divide polygon to offset polygon, and we don't need this now. Let me zoom in a little bit to see what's going on. Vertices, another spelling issue in line 55 here, vertices, save it, uniform, form. And yeah, everything is all right for now. Let me just return these new points and see what's going on. Yes, we have these points here. Let me visualize it. And yeah, we have these newly generated points. And these outer points are the corners of our polygon, while these inner points are the curves, newly generated intermediate curves. So we basically have what we want in this step. And let's keep going on. Then I need to interpolate, or I need to use these 5 points to create a new Nurbs curve. So I can say curve equals to rg.nurbs curve dot create. Input, the first one is true, which means periodic, and the degree is 3, and the points is new PTS. Exclude the last point because I set the Nurbs curve as periodic, so I should exclude the last point. And if I return this curve, I think I will see the newly generated Nurbs curve, yeah, which is this one. Then the next thing is I want to make it jaggy, so I should call another function called jag curve we define here, curve, and the first input is the curve itself. The second input is the plan. Yeah, we have plan here, and the third input is the subdivision number. And this time I want to increase number to 30, and we have this thing here. Maybe we can try to use these points to create polyline, to create the jaggy polyline. And we have here, but you can see there is a problem at this end, because when we are dividing the periodic polyline, dividing a periodic polyline, we will neglect this final point. So in this condition, we just divide the polyline from here to here, and we don't have the closed position, so we need to modify the code in the jag curve to make the first point and last point at the same position, so the curve will be closed. And inside here, let's go to the jag curve function, and I want to add another parameter here with a default value of 0, and I want to set this mode as 1. So we will implement a different mechanism of subdividing, of creating this jaggy curve, this jaggy polyline compared to our first cell. So inside here, I think what we can do is to first append the last parameter, or append the end of the domain into these t's. So I can say if the mode equals 1, which is when I was creating the cell 2, I want the t's append the last value of the domain, which is curve.domain with index of 1. And then inside here, I want to say if the mode equals to 1, our vector is negative plan dot z-axis, because I don't want, in this condition, I don't want the point move along the curvature. Instead, I just want it move along the z-axis of the working plan. So I define this function here, and I can say else here, which is another condition happens on the cell A. If I save it, yes, we have a periodic modification, but I don't really have the jaggy pattern because I should move these two lines out and save it. Then we have a closed jaggy pattern. Now let's see what's our next step. We have this jaggy pattern. Oh, we still need a small circle in the center, and also we need to return this outer line, this outline of the cell. So I can say here, let me see. Let us first create the circle in the center. So I can say the inner curve is the circle. Inner equals to rg.circle, and the first input is the working plan. The second input is the centroid, with the radius ranges from 0.3 to 0.6, and we can return this inner here, I think, and save it. Uniform, FORM. Yes, and we have this inner circle here. We have our curve. I want to convert I also want to convert the curve into polyline. Now it is just points inside it. So I can say curve equals to rg.polyline curve, and put all of the vertices inside here into it. And yeah, we have these no, it's not vertices, it's curves. It's the curve itself, and we have this one. Yeah, actually I already no, sorry, I mean we still need the outline here, right? So I can say outer, sorry, I can say outer equals to rg dot polyline curve with the vertices as I just did. And also I can return this outer polyline here. So we have 3 polylines we want. And let's try to loft them to see are there any issues in creating the new cell. And yeah, we should list item. We should use the list item node here and connect this one to this end. And let's see, 1, 2, 3. The first one is our jaggy polyline, so I'd like to do this, the first one, and the second one. There is some problem. Let's keep working on the next pair of the loft. This one and this one. And let's bake it out to see where is the problem and what we should fix. Preview off, and you can see it's actually twisted instead of a straight loft, because the start point, or I mean the seam of the jaggy of this jaggy polyline is different from the outer polyline as well as the center polyline, or as well as the circle. Sorry. So maybe we should find a way to move the seam or the start point of this jaggy polyline to somewhere very close to the start point of the outer polyline. That will solve the issue. It sounds might pretty abstract, but I think we can just hands on it to see how to fix this problem. And yeah, first I need to change the start t of our the start parameter of our curve, of our jaggy polyline. Sorry. So I'd like to say here maybe, yeah, I can group these lines of code together, and here I can say change seam, and here I will define the start parameter as curve dot closest 0 as e as t point with input of vertices index of 1. So this line of code means I want to put the start point of the outer polyline. Sorry, my English is start getting messy, but yeah, I will try my best to explain everything. So first we need to find the first point of the outer polyline and project the first point to the jaggy polyline to find the perimeter of the closest point. Then we can move the start seam to this closest position. So first thing, we get the start t, and let's print out to see what start t contains. Start t. And we have actually two values. The first one is true. That means the closest point is successfully created or formed. The second value is the t value. Is the t value on the jaggy polyline that corresponded to the closest point. So we just need this t value. We don't need the Boolean value. So we can say 1 here. And then we will change the seam of the jaggy polyline. So we can say change closed curve seam with the t is our start t, and save it, and you can see the first problem solved. Now this outer polyline successfully straight loft with the jaggy polyline. So we need to fix the same problem at the circle here, and we can say inner start t equals to inner dot closest point with the vertices, the same vertices here and the same index here. Then we can just change the seam of the inner circle here. So we can say inner dot change closed curve seam with the start t. Oh, sorry, I should say inner start t and save it. Oh, it's wrong. Has no attribute. Oh yes, I can't do this on the circle. I should first convert the circle into the Nurbs curve. And yeah, my bad. So I should do it here. I should say inner dot to Nurbs curve. And I think now it works. Maybe it works. No. Inner dot to Nurbs curve. Yeah, reassign it, and yeah, we have this this second cell. Let me bake it and see how it works. Preview off, and yeah, let's see. Everything works pretty well. So we have these two cells. The next thing is we need to assign these two cells into the voronoi pattern we generated at the beginning randomly. So this is the last thing we need to do in today's video. And yeah, we are almost there. And let's go to the very end of the code. I will separate this part with the previous functions. I can call this operation. I call this operation, and we can start assigning two cells to all of the voronoi polylines. So first, I need to create new cells as an empty list, and also I need all plans as a list as well. Then I need new bases, which is our newly generated voronoi pattern. It's shifted from this one. The new bases are these newly generated polylines. Okay, so we have these new three we have these three new empty lists. We can start loop over all of the cells here. I can say for poly in cells, and I shall remove all of this below and focus on creating this new lines of codes. I should say vertices and plan equals to move vertices. Yeah, the first step, we move all the vertices, create new polylines, and then we should append the plan to the plans list. So we can say plans dot append the newly generated plan. Then we need to put the newly generated polyline into this new basis. So we can say new basis dot append rg dot polyline curve. Because we just returned these vertices, we need to convert the vertices into the polyline. So we can just input vertices into here, and then the next step is we need to randomly select the cell in the polyline. So we will use the condition called if rand int 0 and 1 equals to 0, which is 50% of the possibility. So the new cell dot append divide what's the function name here? This is the div polygon with vertices and plan. And also if it's not equals to if it's not equals to 1, it's another 50% of possibility. We can say else new cell. This is new cells. Yeah, new cells dot append of set polygon vertices and the plan as well. And at last, mm, yeah, we already have all of this. At last, we just need to update the variable names here. The first one could be new cells. The second one could be new basis, and let's see if this one works. Yes. Now we can see we have our new basis, but the new cells here doesn't show up because the data structure is now IronPython list. It's not in tree structure. So we need to convert from the list structure to the tree structure in the Grasshopper. And to do this, we need to import a new library which is called import. It's not a new library, it's another library, sorry. Which is the import GhPython library dot tree helpers s th, and save it. And at the end, I can convert these new cells to the tree structure. So new cells. Sorry, it should be, yeah, new cells equals to th dot list to tree like this. And oh, it's hidden. And yeah, so we convert from list to tree, and in the parentheses we just put this new cells variable into it, and I think then we will get what we want. Although the pattern is not very radical, so I will prefer to increase the dimensions of this value. Maybe I will increase the height of the ridge, and then I also increase the height of this intermediate polyline in the volcano pattern. So the height here could be 1.0 to 2.0 as well, and if you want, you can keep increasing it until you are satisfied. So we have all the polylines. The last step is we use Grasshopper to generate the solids. So you can see the structure is like this. We can simplify it, so we still need to use the list item node. I shouldn't block the Grasshopper interface, so move it to here, and yes, and now we should increase the index number to 3, and then this first one should be the newly generated curve. This should be the one of the base curve. This should be another one, so we use loft on the first pair, and we also loft another pair like this, and this one, and also we can change the display mode. But before this, I want to also loft the newly generated polygon with the base polygon. With a base polygon. So it looks like this. They are these two. So I think I can do graft tree here, and also graft tree in this end, to make sure their data structure, I think it's better to simplify them. Only one level, it looks good, and we can merge them together, and almost there. 2 in each set. We can loft them. And we have our bases. Then we can merge them together and change the display mode to make all the polygons show up in our interface in a pretty decent looking. We can use custom preview. Sorry, it's to zoom out. Connect it to here and choose the color, maybe white. That will be most powerful one. And see, we have our volcanoes here, we have our ridges here, and we have this kind of uneven distribution and shifted height. So I think that's it for today's video. And thank you so much for watching. Oh, it's another long video. I just noticed I did another over 1 hour long video. Sorry for thanks for your patience, and sorry for my, for my this kind of long video. And yeah, thank you again. Thank you so much again for watching. If you have any comments, any thoughts, please comment in this video, and I will reply each of your concerns. And yeah, that's it. Bye bye.